In a harsh winter climate, many animals are hard-pressed to survive. The land is barren, food is in short supply, yet keeping warm in the bitter cold puts a tremendous drain on an animal's reserves of energy. Many animals have to scavenge low-grade plant material to keep going, but even that can be difficult to find. Large mammals, like the buffalo, tolerate cold because they can store vast amounts of body fat, and their coats are thick, providing good insulation against heat loss. It's the smaller animals that have the hardest time. They lose heat more quickly and can't store much body fat. For some, especially birds, migration away to warmer climes is the answer. But yet another strategy is to disappear into hideouts, to sleep it off. This Canadian ground squirrel, by hibernating, doesn't escape the cold. If it keeps a high body temperature like other mammals, it would still use up a lot of energy. So, how effective is hibernation as a strategy? Physiologist Larry Wang studies these hibernators in their natural habitat. He makes daily treks, even in the winter, to squirrel burrows he selected earlier in the year. But monitoring the behavior of an animal that's hidden several feet below the ground requires a little ingenuity. Over the burrow entrance, he's placed a weather box to protect his equipment from the harsh climate. Air temperatures here in Alberta can fall as far as 40 degrees below zero. A radio receiver picks up a signal from the squirrel below. Very cold weather can interfere with reception, so regular checks are essential. The signal is coming from a tiny transmitter inside the squirrel. It provides a record of the animal's body temperature. This information is carried by cable to a nearby farmhouse, where it's recorded automatically at 5-minute intervals. The transmitter is custom built. Larry gives each one a unique carrier frequency and a resistor that's sensitive to temperature changes. It's working. The device, when coiled up, is compact. The largest part is the battery at the base. Before implanting it in the squirrel, the transmitter is covered in plastic and sealed with wax to protect the animal from any discomfort. The last important step is to calibrate its temperature component. The transmitter is placed in a water bath, and the changes that occur in its tone at different temperatures are recorded. To find the voltage of the transmitter's tone, Larry matches it with one produced on a tone generator. He does this very accurately by ear. By recording voltage changes at different temperatures, he can then plot a calibration curve for the transmitter to convert tones directly into temperatures. Experiments begin in the summertime. That's when these squirrels, known as Richardson's ground squirrels, are found in abundance on the prairies. They're easily spotted. Much of their time above ground is spent eating, but their burrows are never far away, and they can quickly scurry underground. They don't store any food in their burrows, but collect plenty of straw to make them cozy for winter hibernation. Out of the haven of their burrows, they have to beware of predators, like the prairie hawk. And, of course, Larry causes a scare as well, only he's looking for volunteers. He collects squirrels in late summer, 6 to 8 weeks before they go into hibernation.
I'll set one here, and then we'll look for the others. Yeah.
A lot of fresh dirt.
Yeah, okay, that's good. Give me some bait, please. Yeah.
These burrows are hazards for cattle, so farmers see the squirrels as pests to be destroyed. The few that Larry traps escape a much worse fate at the hands of the farmer. They're inquisitive by nature, but will the bait work? Trapped, but it's only temporary confinement. The squirrels recover from surgery in only a few days.
Yeah, that's good.
Occasionally, Larry attaches an additional transmitter to the squirrel's leg before releasing it back into its territory.
Okay, this is where we caught this guy from. Let's go. Yep. I'll release and you let the line go, okay?
He knows the transmitter won't stay there for long, but after it's shed, it still gives him a record of burrow temperature. It's unhindered and unaware of the transmitter in its abdomen. And as long as Larry keeps the squirrel in range, he can find out which burrow it will settle in. The transmitter frequency can only be picked up over a short range, between 8 to 30 feet on the surface and 5 to 20 feet underground. So he needs to be certain of the burrow before setting up his weather box. As the squirrel goes into hibernation, recordings from the transmitter are of lower and lower pitch. We are hearing a gradual but progressive drop in body temperature. Respiration and heart rate slow down too. Amazingly, its body temperature can fall close to freezing, whereas a drop of even a few degrees for most mammals would be fatal. But stay above freezing it must, for in blood cells at this temperature, ice forms. The circulation seizes up. Does a hibernator withstand such a low body temperature right through to the spring? Larry's results show that after several days, the sleep is unexpectedly interrupted. In a matter of hours, the squirrel warms up, a 30-degree rise, and further measurements show that this occurs on and off throughout the winter. Bouts of hibernation get longer and longer, reaching lower and lower temperatures, but come the spring, awakenings occur more frequently again. Each arousal squanders precious reserves of energy. To reach its active body temperature of 37 degrees centigrade, it increases its heart rate and breathing, stimulating the muscles that shiver it awake. It's a gradual thawing. The warm blood takes longer to reach its limbs. But in the coldest part of the year, the animal is suddenly active in the burrow. It may stay awake for up to several hours at a time. But why? After all, it's on a sleep and save campaign, yet it's wasting its reserves of fat when there's no food to eat. So, how much energy can it really save by hibernating? To answer this question, Larry had collected data on the squirrel's metabolism. In large, controlled environment rooms, he's able to simulate field conditions. He uses a simple sawdust test to follow bouts of hibernation. If the sawdust is disturbed, he knows that a hibernator has aroused between inspections. During arousals, these laboratory animals can be regularly weighed to monitor weight loss throughout the simulated winter period. Some animals are implanted with transmitters to monitor body temperature, as in the field animals. But in the lab, Larry can carry out conventional measurements of respiration and heart rate that are not yet possible to collect under field conditions. To do this, he uses a metabolism chamber. Inside this chamber, he can monitor the amount of oxygen used up by the squirrel, and similarly, its carbon dioxide output. This data is fed into a computer, together with body weight and temperature measurements, and from this, changes in metabolic rate can be worked out. The trace here shows oxygen consumption increasing at normal body temperature, and then beginning to decline as the squirrel settles down to sleep. How does his laboratory data relate to his field experiments?
From the field studies, we have measured using radiotelemetry the pattern of hibernation in the field and the precision of body temperature during those hibernation episodes. In the lab, we have simulated the field conditions and measured precisely the metabolic costs associated with the hibernation episodes. From these two sets of data, we have combined and work out an energy budget for hibernation.
Larry's results show that the squirrel, by hibernating, uses only 10% of the energy it would use if it stayed at its active body temperature, a saving of 90% over the winter period. Looking at the energy an animal does use during hibernation, he's found that bouts of entry, deep torpor, and arousal account for as much as half its energy expenditure. The other half is spent while it's awake in the burrow. So, although there's a staggering saving of energy overall, the periods of activity seem to be unnecessarily wasteful.
Why should the animal spend 50% of its energy seemingly doing nothing but remain stationary in the burrow? This, I think, remains as a mystery, but there are many possibilities. One of the speculations I have is that maybe the animal requires a certain period of time during which it can synthesize or resynthesize some of the physiological molecules which are critical for the reinitiation of hibernation.
The bouts of entry and re-emergence from hibernation are exhausting for the squirrel. These periodic awakenings suggest that hibernation isn't simply a passive falling into torpor, but that it must involve a complex regulatory system in the brain. Here's neurophysiologist Craig Heller.
The control of hibernation obviously involves the central nervous system, and as hibernation involves all aspects of the animal's behavior, physiology, biochemistry, it must involve many areas of the central nervous system. This is a very interesting question. We've recently been using a technique to explore the functional neuroanatomy of hibernation. This involves a radioactive form of glucose. You know, glucose is the fuel of the brain. We have a form of glucose which we can introduce into the animal. The cells take it up in proportion to their metabolic activity, but they can't metabolize this form of glucose, so the radioactivity stays in the cell. The accumulation of radioactivity in the cell then is a measure of the metabolic activity of that cell. So if we look at, let's say, the entrance into hibernation, and then we section the brain, those structures which were most active during this phase of hibernation will have the most radioactivity, and that will show up in the autoradiographs. So, the brain has to be sectioned in a cryostat. The sections are mounted on glass. Then a sheet of X-ray film is placed over the tissue, exposed for several days, usually a week or even 2 weeks. When the film is developed, you can see images of the tissue in which darkness represents areas of high radioactivity and lighter areas represent areas with less radioactivity. So we can then look at an individual section and we can ask, was this structure active during the entrance into hibernation? Here we have some blow-ups of sections from the brain showing the relative patterns of uptake of this form of glucose. And we can compare, therefore, a normal animal, an animal entering hibernation, an animal in hibernation, for example. This particular collection of sections shows a very interesting result. There is one nucleus. It's the only area in the brain which actually increases its activity during hibernation. In the animal entering hibernation, this structure becomes very black, indicating that it's taking up lots of glucose, taking up lots of radioactivity. Here's a blow-up of this section showing this nucleus in the brain. We think that this is probably receiving thermal information from the face. It's allowing the animal to sense the actual ambient temperature in which it's hibernating. Here's another example of a result, once again comparing a normal animal, an animal entering hibernation, and an animal in deep hibernation. This is a section from a brain that was entering hibernation. We have the suprachiasmatic nucleus, which has been referred to as the master clock of the brain. It's the basis for circadian organization, timekeeping functions. That area remains active during hibernation, indicating that the timekeeping functions of the brain are not abandoned during hibernation, but the animal retains a temporal organization to its functions.
We've been looking at sections taken a few millimeters from the front of the brain. This is an area that we might expect to remain active during hibernation, because just above and behind the suprachiasmatic nucleus is the hypothalamus, the site of the body's thermostat. Craig has shown that this thermostat still functions in the hibernator. But as the animal enters hibernation, its set point is progressively lowered. That is, the alarm temperature at which the animal responds to cold decreases, but it stays above freezing. So, while preventing the hibernator from shivering away its energy reserves, the thermostat still protects the squirrel from fatally low temperatures.
The interesting question then was, how could such a broadband thermostat evolve? So you can ask the question, what general mammalian phenomenon involves a decline in the regulated body temperature? Could this then have been a pre-adaptation that evolution could have worked upon to produce mammalian hibernation? And there's one general mammalian phenomenon, if you think of it, during which body temperature is regulated at a lower level, and that's sleep. When you go to sleep at night, the thermostat of your hypothalamus is reset to a slightly lower level, and you're actually regulating body temperature a little bit lower while you're asleep than when you're awake. We can then think about hibernation as a possible extension of sleep. A given bout of torpor, how does this relate to normal mammalian sleep? We've done some experiments in which we have recorded the EEG of animals going through bouts of torpor. This is a polygraph recording of a ground squirrel that's not hibernating. The three traces here are the EEG, recorded from electrodes in the cortex of the animal's brain. The lower trace is the EMG and EKG. The muscle activity is the solid red area in the center of the trace, and the heartbeats are shown by these high spikes. The patterns seen in the first portion of this page represent wakefulness. The cortical EEG is fast and low amplitude, there's lots of muscle activity, and the heart rate is fast. At this point, the animal falls asleep. We then see the EEG waveform characteristic of slow-wave sleep. It's much slower than the wakeful pattern. The amplitude is higher. There is much less EMG activity, and the heart rate slows down a bit. The animal stays in this form of sleep, slow-wave sleep, then for several minutes. Now, during the entrance into hibernation, this is the waveform that we see predominantly, that of slow-wave sleep. Finally, we get over to this page and we see a transition again. In this case, the animal is going from slow-wave sleep to REM sleep. This is an interesting state. There is considerable skeletal muscle inhibition, so the animal is essentially paralyzed during REM sleep. Their REM sleep gets its name because of the rapid eye movements that occur during this state. If you think of your dog sleeping on the floor at night and all of a sudden its legs start to move, if you look at its eyes, the eyes are darting back and forth under the eyelids. And this is REM sleep. It's when we have our most vivid dreams and nightmares. An interesting aspect of REM sleep is that the thermoregulatory system is inactivated during REM sleep. So it would be attractive to think perhaps that animals could enter hibernation through REM sleep and turn off the thermoregulatory system. But they don't do this. As the animals enter hibernation, REM sleep decreases in frequency and slow-wave sleep increases, so that a bout of hibernation is actually mostly slow-wave sleep. Now, this makes an interesting correlation with the thermoregulatory studies. Animals regulate their body temperature during hibernation. They regulate it at a successively lower and lower level, and they're in a state of slow-wave sleep. And we know that all mammals, the hypothalamic thermostat is reset to a lower level during slow-wave sleep. So this makes a very nice evolutionary sequence then. Hibernation could have evolved in animals living in a seasonal environment which lowered body temperature during slow-wave sleep. Selective pressures could have favored decreasing depth of sleep and decreasing body temperatures during bouts of slow-wave sleep, eventually grading into deeper and deeper torpor, which we think of as hibernation.